Hello, Berliners and people of the internet. Thank you for joining remote edition of Elixir Berlin, uh, version 73. I hope that you and your family are safe. Just a quick introduction how the today live stream is going to work. If you are watching this live stream, it means that you have joined half of the party. The other part of the party happens in the Discord channels. And we have one Discord channel for you to join. You can ask your questions at the end of each talk and also hang out with other member of communities. I tried to give you a few seconds to just copy this link. You can also find this link in the YouTube video description. For the agenda today, we have one main talk by Luis, creator of Gleam language. You might know him for his Elixir packages like Mix Text Watch and also Dagma and XFMT. And here he is with his relatively new work, the Gleam language. And after that, we also have a lightning talk by me about the package that I found a few days ago. It would be quite short. So as I mentioned, at the end of each talk, the speakers answer your questions. Make sure to write it down in the general channel, or you can also ask him directly using the voice channels. Without further ado, let's get started.
Hello everyone, I'm Louis Purefault. Thank you for coming to my talk. I'm sorry this one has to be pre-recorded, but since the lockdown has started, my internet's been quite unreliable, so I haven't been able to stream. But I hope you enjoy it, and I'll be around afterwards to answer any questions. Thanks. Alright, so I'm here to talk about Gleam, which is a new statically typed programming language for the Erlang virtual machine, for the Beam, that I've been working on for the last 2 or 3 years. So Gleam draws inspiration both from Beam languages, such as Elixir and Erlang, and also ML languages, such as Haskell and Elm. So in this talk, I'm going to take a look at these two language families and see why I think they're fantastic to work with. We're going to take a look at some of their strengths, some of their weaknesses, and how Gleam, this new language that I've been working on, attempts to bring together some of the best traits of both. Okay, question number 1. Why Erlang? So I think one of Gleam's greatest strengths is that it can pass to Erlang and as such can take advantage of all the wonderful things that the Beam has to offer. As this is a Beam conference, I'm sure we're all very familiar with why the Beam is excellent, but just to make sure we're all on the same page, I'd like to go through a few of my favourite things about the virtual machine. Erlang is slightly unusual for an older functional programming language, in that it originated largely from industry rather than from academia. So back in the 1980s, the telephone company Ericsson were looking for their ideal language for writing telephone switch firmware, and from this real-world need, Erlang was born. A telephone switch is a piece of hardware that connects phone calls. So when a person dials a number on their phone, the local switch identifies where the call is attempting to connect to, and then helps to create a complete circuit between the caller and the receiver. Back when the telephone was first invented, this would have been the job of a person, sitting at a switchboard, physically connecting different circuits with lengths of wire. And sometime after that came automatic mechanical switches that didn't require a person to make the connection, but were still hooking up physical circuits. And then later still came digital switches, which would create virtual circuits within software. And so it was for these digital switches that Erlang was created in the 80s. So in order to meet the unusual requirements of the telephony hardware, Erlang and the Beam, as an extension, developed some rather novel features. For a telephone switch to be useful, it needs to be able to support multiple phone calls at the same time. Now, if you had to wait for your neighbour to get off the phone before you could make a call, I suspect telephones probably wouldn't have ever caught on. And so because of this, Erlang needed to have excellent concurrency features so that one switch could handle many calls at once. Any program written in Erlang needs to be able to trivially perform a great number of tasks at the same time. This was such an important feature, they ended up naming the language after it. As well as being a programming language, an Erlang is a unit of concurrency. It measures seconds per second. So a telephone switch that can hold 100 simultaneous calls can support a load of 100 Erlangs. And the unit, Erlang, was named after this chap, Mr. Agner Erlang. He was a Danish mathematician who in the 1980s invented the Erlang formula, which continues to be a foundational element in the analysis of telecommunication networks and concurrent systems to this day. So by all accounts, quite an impressive person and a good bit of history for our ecosystem to have a link to, I think. Right, fast forward 100 years back to the present day. When it comes to concurrency, the beam can definitely scale, but it's not good enough to merely be possible. Ericsson needed this to be relatively easy so that firmware developers could be as productive as possible. Asynchronous programming is notoriously difficult, especially if you're working with tools like locks, callbacks, shared mutable states. So the creators of Erlang went down a very different route. Rather than having a small number of threads, each handling a large number of concurrent tasks, in the Erlang world, we use a great number of threads, but each thread only has one single task to perform. If each thread only has to do one thing, it can be written in a sequential fashion. And so, to paraphrase the late Joe Armstrong, one of the creators of Erlang, it is difficult to write a web server capable of handling 2 million sessions. However, it's much easier to write a web server capable of handling a single session and then run 2 million copies of it. To support this high level of concurrency and to use this many threads, Erlang threads are not implemented as operating system threads. Instead, they are lightweight threads, and these run on their own scheduler that is part of the beam. Sadly, processors in telephone switches couldn't be completely isolated from each other. There's always going to need to be some element of synchronization and communication between threads in any program. So rather than using shared state or locks to communicate with each other, Erlang processors communicate by sending messages to each other. And what's more, processors within a telephone switch don't just need to talk to other processors in the same switch, they also need to talk to many devices all over the telephone network, as calls are going to be routed through multiple different pieces of hardware to get to their destination. So to facilitate cross-network communication, the beam has distributed computing features built into it. When sending a message, it doesn't matter if the receiver is a process running on the same instance of the beam, or maybe it could be a process running on a different instance of the beam, but still on the same computer, or it could be on a completely different computer that's connected by the network somewhere. The processes can still send messages to each other in the same way. So distributed computing is built into the beam itself, and a typical beam program written in Erlang or Elixir can be turned into a distributed program that runs on a cluster of networked computers with minimal effort. Perhaps most excitingly, at least to me, Erlang processes act as error bulkheads, meaning that when something does go wrong and your code crashes, the problem is contained to the smallest possible subsystem and does not impact any of the other work undertaken by the program at that time. So an Erlang program that takes advantage of this property can self-heal by restarting the process and try again, hopefully succeeding now that any corrupt state has been shed. So in this way, the beam is much like Kubernetes, the popular container orchestrator from Google. But what makes the beam different from Kubernetes is that this state shedding can happen at a much more fine-grained level. We don't need to lose the state of the entire running program and all of the concurrent requests being handled by it. Instead, we lose just the single process that had the problem. And so I like to think of the relationship between the beam and Kubernetes as being similar to the relationship between Kubernetes and data center failover. They're similar, but they operate at different levels of abstraction. and I think they can complement each other quite well. So the Beam was created with the problem of telephony in mind. But it turns out that what was once quite a niche set of problems is actually quite commonplace today. Concurrency, parallelism, distribution, achieving a consistent low latency, and fault tolerance. These are characteristics we want in network services today, regardless of exactly what they do or what language they're written in. And so the Beam, almost by chance, has become an excellent program for building web applications or databases or message brokers or many of these other things that we as developers, particularly web developers, have to deal with on a daily basis. So now we've seen a little of why I think the Beam is a wonderful platform, but I've not answered the question of why am I creating a new language at all? We've already got several fantastic languages on the Beam, such as Erlang and Elixir and LFE and more. Why have I spent all this time creating Gleam when I could use one of these? And so to answer this question, I'd like to take a closer look at the Beam's self-healing properties and how that impacts as developers of software and as operators of software, because we have to run the programs that we make. So hypothetical situation, it's a normal day at the office and I've got a change to make to an application. Perhaps I'm adding a feature, maybe we're removing a bug. It doesn't matter, I've got to make some sort of change to the code. So I start by editing the code a little, by making some changes. Once satisfied, I run the compiler to build the application, which completes successfully, reporting no problems. After that, I run the unit tests on my laptop to make sure I've not broken anything, and when they come back green, I push my changes up to GitHub. Once I've uploaded my code, it triggers a build on the CI server. It runs all the unit tests, all the integration tests, maybe it runs some linters like Elvis and Credo, and it tries to spot any mistakes that I've made. And if all those checks pass, it then deploys the new application version to a staging environment. And on the staging environment, I can manually test the application and demo the new behavior to stakeholders who, if satisfied, give the green light to continue. Meanwhile, on GitHub, the code is reviewed by some of my peers, by some of the other programmers on the team. They may have insights and context that I do not, so they know how to do something differently, or they may spot a problem that I can't see. But they're happy with my changes, and they approve it, and so the code gets merged into master, which triggers another CI build. All the tests and linters are run again to ensure that no problems were introduced in the merging process. And then lastly, once the tests have passed, the code is then deployed and released into production and to the users. Satisfied with a job well done, I can go to lunch or go home or go about my day. But then, disaster strikes. Users are reporting that the application is no longer working as intended. Right at the very beginning of the process, when I was editing the code, I made a mistake. I introduced a bug. And each one of these steps has failed to detect the problem, and now the bug has snuck into production. So luckily, the application is written in Erlang, so the impact of the problem has been minimized thanks to the fault-tolerant properties. But there still is a problem. Something is wrong with production, and now I have to fix it as a matter of urgency. In this instance, the problem was discovered just a few hours after I made the mistake, so the change is still fresh in my mind, not too difficult to correct. But that's not always the case. Depending on the culture of the company I'm working at, it might take days or weeks for the change to be deployed to production. One of my last jobs was working at a bank, and I think it was about 2 months before I managed to get anything to production. Or alternatively, it might have been deployed, and then it might have taken even longer for users to discover the problem, because it might have only happened in a small set of scenarios. Worst case, the code has been in production for months or maybe even years, and the writer of the bug has since left the company and gone somewhere else. And so now I'm left trying to fix a bug with unfamiliar code that I've never seen before. Maybe I don't even know what it does. The larger the gap between a mistake being made and a problem being detected, the more difficult it will be to fix. Of course, this isn't the only factor, but it is an important multiplier in terms of how difficult it's going to be. So Erlang gives us the tools to tolerate mistakes, and it gives us tools to debug them, but they largely only help us once there already is a problem in production. And that time cost and that loss of familiarity is far from optimal. It's in fact quite expensive. So what I really want is for problems to be detected here, immediately after the mistake was made. What I want is for the feedback loop to be as fast as possible so we can spend less time doing exploratory, investigative work, such as debugging problems in production, and more time iterating, actually providing business value and having fun making things. So Gleam aims to provide this fast feedback loop by introducing a type system inspired by those found in the ML family of languages. And why these languages? Because I believe that these are the languages that currently do the best job of providing this fast feedback loop. So let's take a look at some examples. So Messenger is Facebook's web chat program. It has 1.3 billion monthly users. Back in 2016, they started converting the web client from JavaScript to a dialect of OCaml called Reason. And a year later, 50% of their code was written in Reason, and they had this to say. Messenger used to receive bugs on a daily basis. Since the introduction of Reason, there has been a total of 10 bugs. That's during the whole year, not per week. Refactoring speed went from days to hours to dozens of minutes. So that's quite an impressive statement. Next we have No Red Ink. They are a company in the United States that provide educational software. And back in 2016, they started adding Elm to their CoffeeScript web application with great success. And in 2018, one of their engineers, Richard Feldman, posted this tweet. After 2 years and 200,000 lines of production Elm code, we got our first production runtime exception. In that period, our legacy JavaScript code has crashed a mere 60,000 times. Again, quite impressive. But that's not to say that the engineers at No Red Ink and Facebook are without error. They're going to make just as many mistakes as you or I. The key takeaway here is that they have a way of discovering and fixing their mistakes before they get into production. Lastly, Lumi. Lumi are a company that provide custom, eco-friendly, branded packaging for online stores. And in 2018, they started converting their JavaScript front-end into a PureScript front-end. And after a few months of PureScript in anger, engineer Brandon Martin had this to say. I've had such a positive experience with little mental overhead, and I have total trust in the compiler. I implemented an entire page with a list of data, filters, search and pagination, and it worked first time. What I really like about this quote is this idea of a feeling of trust in the compiler, in that it is something that can be relied upon. With Gleam, I really want to create this experience on the beam of the compiler being like a pair programming partner, and it is there to help you by catching mistakes as quickly as possible and providing additional insight. So how do these languages achieve this? They do it by having a compiler that is capable of analysing the code for inconsistencies and providing precise feedback to the programmer, detailing every place where a problem may arise. So once the programmer has this tool, this ability to discover all of the possible problems in an application, they can change the way that they approach writing code. So the new system becomes the programmer first makes an edit which informs the compiler of the kind of change they wish to make. So for example, perhaps a function has been changed to sometimes return a null value under certain circumstances. In languages like Erlang, that doesn't have this static analysis, it is now up to the programmer to find all of the places in the codebase that need to be updated to handle this new nullable value. In Erlang, we might do this by using a mix of existing unit tests and just a familiarity with the codebase, knowing where this function is going to be used. And that would help with this manual change. But in Gleam and ML languages, the compiler outputs a to-do list of inconsistencies, and then the programmer just goes through each place in the list, fixing them one by one. There is no longer any need to do any discovery work. State the change you wish to make, and then the compiler shows you how to integrate that change. And as I've said before, you can achieve this same thing with a set of unit tests if they're robust, but I think that having the compiler do it via static analysis has a few advantages. We don't have to worry that perhaps our tests aren't comprehensive enough. Maybe they miss some edge cases. The static analysis always covers all edge cases and always covers the entire code base. The compiler gives it to us for free. It even covers code that is hard to test, so code that performs I/O, that interacts with external services that maybe we don't have available in tests. Secondly, this static analysis is fast. A large codebase can be checked in seconds or fractions of a second, while tests could take minutes or not even be possible to run on your local machine. Thirdly, the compiler can provide the precise location of the cause of the error, while tests can only give you the location of a resulting symptom. Once a test prevents an error, it is then up to the programmer to determine if the problem originated where the error was detected by the test, or it's somewhere further up the chain. It could be somewhere else entirely. With static analysis, the programmer doesn't have to do any discovery work, which rapidly cuts down on the amount of time you have to spend developing your program. It might seem that with this ML-style error detection, the Beam's runtime fault tolerance and error handling features are slightly redundant, but actually I think they can complement each other quite nicely. The error detection means that we are aware of all the places where the problem can occur, and then we can make an explicit decision about how we want to handle it. And because the decision of how to handle an error is now explicit, the compiler can tell if a crash is intentional or if a mistake has been made. Let's look at some examples. Imagine a problem that is caused by a mistake on my part as a programmer. So for example, here I'm trying to reverse a binary string, but I'm using a function that reverses lists. In this case, once the error has been highlighted to me by the compiler, I realize I've made a mistake, and then I go and fix the bug. Erlang's fault tolerance isn't the right tool here. If a trivial mistake has been made, I want to find it as quickly as possible, and I want to fix it. Another situation in which errors might arise is when dealing with user input. Here we have a handler function from a web application. It takes a request data structure and it returns an appropriate response. As part of this, it reads some data from the body, and that data has been encoded in the JSON format. The problem here is that the request body might not actually contain valid JSON. We can't always rely on getting the correct input from the outside world. Once this problem has been highlighted to us by the static analysis tooling, the most practical thing to do is to check whether the JSON is valid or not. If it isn't, we can then return the error to the user, informing them that they have made a mistake, that there's something wrong with their JSON encoding. If we can pass the error back up the chain to the user, that's often the best thing to do. Erlang's fault tolerance isn't the right tool here either. So another example. I used to work at a startup that did video transcoding, and we had a lot of jobs that ran in the background, and as a result, they didn't immediately have a user attached to them. One of the jobs looked like this. First, it looked at some metadata for a video from the database. Then it created some thumbnail images for the video. And lastly, it transcoded the video. Each one of these steps is expected to always succeed according to our business logic. But because of the nature of programming and just the universe in general, there's a very real chance that one of these things could fail. A faulty hard drive could have corrupted the video file, or perhaps the unreliable network causes the database lookup to fail, or there could be a bug in the third-party video transcoding software that we're using that causes it to crash. So the ML-style error detection here forces the programmer to acknowledge these potential problems, and we end up with this verbose nested code. After each step, the programmer has to check to see whether it failed, and then do something with the error. This code is much less clear than the previous version, and it's much harder to tell what the actual business logic is here because it's being obscured by the error handling. We could rewrite the job using some higher order functions that extract some of the conditional logic. This removes the nesting, but now the reader needs to be familiar with all of these combinators that's been used in this code, and the code is much more complicated than what we started with. And to make matters worse, it's not even clear what we should do with the error once we have it. There's no user to return the error to. perhaps we need to create some sort of error logging system. And at this point, I'm really hoping that you're leaping forward to say that there is a better way, there is a better approach than this defensive programming. And that better approach is offensive programming. Here is where we take advantage of Erlang. If your business logic says that something should never fail and that you have no way of reasonably handling the failure, don't check for the error. Instead, make the assertion saying, in order to continue, no error must have happened. And if there was an error, we crash the process as there's no sensible way to continue at the process level. And now, the Beam's fault-tolerant properties come into play. The crash is logged and reported, and the process can be restarted as required. The rest of the program continues running without problem. And so as the Erlang saying goes, let it crash. So the ML type system helps us find all places where an error can happen, and then we can categorize those errors into two different groups. Errors that are expected within our domain, such as invalid user input, we can deal with them locally using conditional logic. Errors which are exceptional and happen outside of our domain, such as data corruption, hardware failure, we can handle them in a non-local fashion using processes and the Beam. If an error is truly unexpected, it shouldn't get... Hello everyone. Sorry, I think that got cut off slightly early, so we missed the very end of it. But I think you got the general idea of what the Gleam philosophy is about. This idea of using a type system to ensure that we have the tightest feedback loop possible, and to make sure that any times it can crash, that is a deliberate choice rather than it being due to an accident. And then for the rest of the times, when there's a situation in which it's truly outside of our control and not something we can reasonably recover from, so it is truly exceptional, in that case we can use Erlang's fault-tolerant properties to do something. Yeah, so, and then after that I was going to say a few more things, such as we've just had a latest release, the 0.10 release, which has been quite exciting because it has been done largely by people who aren't me. So the community is continuing to grow, and we've got some exciting new features such as module constants and bit string pattern matching. And we've used that to implement some silly things like an emoji library. What else did I have recorded in that talk? Oh yes, and another thing is that Gleam is a community project, so please do get involved if you're interested in getting involved. If you want to contribute code, that would be cool. If you just want to write some Gleam for yourself and then tell us how you find the language, that would be super appreciated. Or if you want to share ideas, if you've got some ideas of what would make Gleam a really exciting language for you, then definitely jump in the IRC channel or jump in the GitHub issues. And lastly, Gleam is my full-time work at the moment. So if you or your employer would like to help support me in doing this, because I think a lot of us do want to have types on the Beam, then please consider sponsoring the project on GitHub issues, GitHub sponsors, not issues. I'm very lucky in that there's currently enough people sponsoring the project that I can actually pay my rent, which is something I didn't think we'd be able to do like a couple of years ago. So last time I gave this talk, one thing people said was there wasn't. And please do feel free to ask any questions in the Discord, and I will answer them. But one thing that people said last time I gave this talk is that there wasn't enough Gleam in it. So I thought I would just show you a few examples so you get an idea of what Gleam is like and how it compares to Elixir, because this is probably the common language here. So here we've got a fairly standard looking bit of Elixir code. So the first thing it does is it passes some arguments in order to get an ID out, and then it uses that ID to fetch a user. And after that, we call this renew subscription function with that user, and we get back some subscriptions. And then we just return the user and the subs. But it's a little more complicated than that because we're using a with expression. So in case anyone hasn't come across these, the way this works is it always makes sure that this is the pattern of the data, this is the shape of the data, this is the expected data from this function call, from this expression. If it is that pattern, then it goes on to the next line and it can continue. But if it doesn't, then it returns and it gets passed back to results. So this is a really useful way of saying this must succeed, and also this must succeed, and also this must succeed in order for us to progress down the happy path. And then we can do something with either that fully succeeded value or one of those incremental fail states along the way. So in this case, it's sort of monadic. And so here we just pattern match it again using a case statement to say thank you to the user if it succeeds, or if it fails, we will say something went wrong. So here we've got exactly the same code in Gleam. There's a few differences. So for example, we're using curly braces instead of do end, which may be slightly controversial with the Elixir people. But we originally used to have ML style syntax, very similar to Haskell or Elm, but people actually found that kind of confusing. So we ended up going for some more C, JavaScript, Scala style syntax instead. And another thing is that when we use a module, we explicitly import it beforehand. This has two purposes. First off, it makes it a little clearer where things are coming from, but it also helps the compiler work out what the relationships between the different modules are, so we can do type checking, compilation a little bit faster. So the important thing here is that Gleam does have a with. It does have something like Elixir's with, and that is called try. And so here it is. Normally in Gleam, when you define a variable, you say let, and then you say the variable name, and then you say equals, and then the value. But if it is try, it works similar to with. But the key point being, rather than specifying a pattern here that has to match, it was always what we call a result type. And a result type is the same as Elixir's error OK tuple. So in Elixir, it would be type results of success and fail is equal to either OK of success or it would be error of fail. So that's a pretty common trait in very common thing to do in Elixir. So in Gleam, we would write it like this. We would say this is a type. We're going to call it results of success and fail, and it's either an OK or it is an error. So we define a type, we've got two constructors, an OK constructor and an error constructor, and this compiles down to exactly the same code that you would use if you were writing this in Elixir, which means that this type has compatibility with all the libraries and all the code in the Erlang and Elixir world. So in this way, we're designing the language so that it can integrate really well into existing Elixir and Erlang code bases, but it's also going to have lots of extra functionality. So for example, because we have declared this as a type, the Gleam compiler can always make sure that anytime you say that something is going to be a result, for example, if you use try here, we are telling the compiler this is going to be a result. And if you've made a mistake in your code so that it might not be a result, it might be something else, the compiler will say, well, hold on, there's something wrong here. We've got to fix it before we can continue, which is really helpful because it means that we can have a little more confidence in what we're doing, and maybe we don't have to write quite so many unit tests, and we can iterate a little bit faster, I hope. So there you go. That's the difference between with and try. They're quite similar things, really. But it doesn't have an else clause. So the other thing I'd like to show you is some error messages, because error messages are awesome. Error messages are really important. If I pick up a new language and it's got rubbish error messages, I have no idea what's going on, and it just feels a little bit unfriendly and it's hard to get into. But languages like Elixir do a really good job of making the error messages, particularly later versions of Elixir, making them quite friendly. So I'm hoping to go even further with that with Gleam, because I want it to be even better. So here we've got some code. It defines a function called add that takes two values, A and B, and it adds them together. And even though I've written no type annotations here, this is a 100% type safe program, because Gleam is clever enough to work out that if you try and add two things together, well, they've got to be numbers. So it ensures that they're numbers for the rest of the code. So here we add 1 and 2. That should be fine. Here we add 1 and 2, but 2 is a float. What's going to happen there? Let's find out. So if I build it using Gleam build, compile super quickly, and then it says, oh, there's a type mismatch. This is meant to be an int, and this is meant to be a float. And it points out exactly where in the code I've got a problem. So it says line 7. Okay, well, let's change that. What if I gave it a list? Oh, my phone's talking to me. What if I gave it a list of floats? What would it do then? It would say, oh, this is a list of floats. So yeah, always make sure things are correct. And as you can see from this, we have generics. So this isn't like Golang. We have some more complicated typing features like polymetric polymorphism and generics and that sort of stuff. So there you go. That's what I wanted to show. I think we've got a question. I was wondering why the syntax was quite different from Haskell. Yes. So as I touched on earlier, we originally had a more Haskell-like syntax. It wasn't super like Haskell. It was kind of like it, but we opted to go for something different for a couple of reasons. First, people weren't used to that syntax, and I personally quite enjoy it. I like C-style syntax, I like Elixir syntax, I like Haskell syntax. But some people found it really hard to get into, and Gleam aims to be a really friendly language first and foremost. We want to get as many people on board with Gleam, but also with Erlang. We want people to be using this stuff, so we want to make sure it's super friendly. So we moved over to something that was more accessible. The other thing is that when you have got a syntax that looks extremely like an existing syntax, people start asking, hey, I could do this in Haskell, why can't I do this in Gleam? In the same way that I think a lot of people were confused coming over to Elixir from Ruby. They were saying, why can't I do this in Elixir when I can do this in Gleam? How do I can do this in Ruby? How do I make an object in Elixir? And that was confusing to some people. So we've very deliberately moved ourselves a little bit away from Haskell, because we're not Haskell. We don't have type classes. We don't have auto currying. We target Erlang. We don't target native code. It's quite a different. It's an impure language. There are side effects. We can send messages to processes. We can print things. So we wanted to make sure there's a bit more of a gap from Haskell in that case. What's the status of gen servers and other OTP stuff? Right. Okay. So this is super important, because without gen server and such, Erlang isn't quite as good, is it? I'll just leave you waiting for a second. So, if you've ever looked at, a lot of people say it's impossible to type processes, and I think that statement is both true and false. So it's true to say you cannot type all of OTP as it stands today. That's not possible. You can't type all of the patterns we use. You can't type all of the patterns that you're going to find in typical Erlang code bases. However, there is a subset of OTP that can be typed. So if we restrict the framework to this subset that can be typed, we will have something that's both practical and pragmatic and useful, but it will also be type safe. And we're taking inspiration from things like typed Agner, which is the active framework for Scala, which is type safe, and it's very much inspired by OTP again. Let me just quickly, I don't want PowerShell. Let me just quickly open some of our experiments into OTP code. And so yes, we think this is very possible, and Peter Saxton, the chap who wrote the Elixir web server ACE and the framework Rax, has moved on to Gleam, and he's making a web server and framework for Gleam, which has lots of type-safe OTP code. So I'll just quickly show you an example of some. My editor's being very slow because I'm streaming, so one second. So here we go. Here is the current state of the art for a Gen server alternative, but written in Gleam. So this is like we're called it Actor at the moment. That name may change, but it's very similar to Gen server in practice. And in the same way that you define two callbacks on a module to implement a Gen server, we say you implement two fields on a record, on a custom type. So we say there's an init, which is like init, and then we have a loop, which is a more general version of handle call and handle cast, because it wraps both of them together. And so by defining these two things, you can start an actor, and it returns an OK tuple the same way you would in Elixir and Erlang, and then you can pop that new supervision tree, and you can call all the usual system debugging functions like get status, and that'll work. So there you go. We've got still very young but working bindings to OTP. It doesn't actually bind. It doesn't actually build on top of OTP. It's rewritten from scratch in Erlang, but it's compatible with OTP. Next question. So, taking into account that some pure languages inspired Gleam, why did you choose to keep the language impure? Right, so Gleam's very much inspired by Haskell and Elm and these languages that are pure. But Gleam doesn't aim to be pure because it has some different design goals. First and foremost, we want to be a typed Erlang-like language. We don't want to be a beamy Haskell language. We want to be a typed Erlang language. So we're less interested in purity and type classes and monads and all that stuff. Even though it's really fun, we're mostly interested in making something that's quite similar to Erlang. And we also want it to be as approachable as possible. And the kind of things that we want to build, like databases and web server backends and all this sort of stuff, they do a lot of I/O, and I don't think we have the tools for modeling that in a pure way, in a way that's very accessible and very easy to pick up yet. One thing that we, I think, will likely have in future is an effect system, but it won't be in the type system, as it were, but we will have the ability to, in the compiler, quite easily track to see whether functions are pure or impure. And this is really useful because you then have a way of performing impure things but controlling them. So you could annotate a function and say this function must be pure and any function it calls must be pure. I don't want any side effects here. So you could use this to annotate your view layer in your web server, and that would work really well. But it would, because it's not in the type system, it would mean you don't have to do things like muck about with an IO monad. It would just be transparent to the user. You write perfectly normal code, and then you can later turn on this extra strictness if you want. And it would just say, yeah, you succeeded or not. But you don't have to flat map on an IO value to dispatch side effects and that sort of thing. Do you think developers must know concepts such as functors, applicatives, monads, etc. to be able to write great Gleam code? No, because none of those things are in Gleam whatsoever. It's a very simple, small language is the goal. and we don't have higher kinded types, and we don't have type classes or traits. So it's not possible to represent, well, it's not possible to represent such generic abstractions in an implicit way. You could implement them by in the desugared form by passing around a record of those functions, but it would be a lot more complicated and probably less fun. And while it's super powerful, those patterns, I think there is a lot of value in very simple code. I think having code that isn't super generic, but you can look at it and say, oh, look, that is a list. And I am doing this with it. I'm using filter and map and reduce. That sort of level of code is a good level of complexity that I think works for practical, pragmatic language. I want people who are familiar with Elixir and Erlang to be able to pick up Gleam pretty easily. Would you suggest using Gleam in production, and when is it planned for a 1.0 release? So the tricky thing about using Gleam in production right now is that there's not much in the way of an ecosystem. There's very few libraries. Our OTP library is relatively young, and oops, sorry, just my internet just went for a second there. So the libraries are very young, and there's not much choice out there. We do now have a web server built by Peter Saxton, and he's building a web framework, but you would be on the bleeding edge if you were to use it. So Peter, for example, does have it in production, and I think the majority of his app is now written in Gleam. But for most people, it probably isn't ready yet. It really does come down to what your risk profile is and what the risk profile of your company is. But as a core language, it's super solid. We're not going to do any major breaking changes, and it runs on Erlang, so the runtime is super robust. And also, if you don't like Gleam in the end, it outputs very code that looks very human. It outputs very human looking Erlang. So you could decide not to use Gleam, and you can just continue with the generated Erlang code. Any plans to compile to Beam binary rather than Erlang source code? No, we're going to continue to go via the Erlang compiler. Elixir actually does compile to Erlang, and then it runs the Erlang compiler. I think this is really good because you get all of the optimizations of the Erlang compiler. The Erlang compiler is excellent. So rather than try and replicate all of that work that they've done, we're going to leverage it by using their compiler within our compiler. We're going to do a little bit better job of hiding those files, because at the moment, if you make a Gleam project, it spits out some Erlang in a folder, and it's quite easy to see what you've got there, and that's nice because you can see what it's doing. But it's sort of like, why is this here? Why should I know about this? And if we hide it away a little bit more, I think it'd be a slightly cleaner experience. So tooling is something we're working on for the next release. And when is version 1 planned? Not yet. We've got a lot of time. We've got a lot of things to work on, a lot of things to improve, and I don't want to rush to version 1. Because once we hit version 1, we really can't change much anymore. I would like to be confident.
Hello. So Thank you, Luis, for your great talk. I'm going to uh, start my lightning talk. Just let me see if it works. Yep, perfect. So my lightning talk is about implementing Ecto queries in while. I didn't spend much time on picking the title, so maybe the title is a bit off. But the thing that I always deal with when I start a, let's say, Phoenix app is its context and the way to query data from database. Of course, so the problem is I want to query the post, but I want to be flexible in part of my application, my controller to load different type of data based on the filtering, pagination, and so on. So one way that one person might do it is just returning the ecto queries and then querying the data on the controller, which of course is wrong. But the way that most of us are doing is this approach is, at least if you don't want to add any customized function or so on, you are going to create a specific functions in your context that returns a specific type of queries. If you want to post with all authors and comments, you make sure that your query does that. And now if you want the post with all authors of the post, you create a specific one. Now you can use this function specifically on the place that you want. Some people might say that's a good approach because then your intention is clear. Your function is not going to be used in multiple places. But I was wondering if we can do better. If we can, in the controller, I just want to say I want comments and author, and maybe the date or pagination. How would it look like? I did some, this is a mayor. So I did some researches and this is what I would like to do. For example, I like to say that I want to all the posts and include the authors and comments for me. And the thing that I found that is a quite young project and not much of, I guess, unknown project. The name is Token Operator. The name might put you off because it doesn't relate to any core improving your query or your use it in context. But this library does a general thing, and what it does is it helps you to organize the parameters that you pass to a function. It could be an ecto query, it could be a validation in some part of your code. So the way that it works is it has only one global function or one main public function. The name is token operator maybe. The naming, I guess it could improve, but what it does, you pass the post struct to this token operator maybe, and you also pass the options. So if in the bottom your option has include or has a date to filter on, you can do a pipe and apply the filters and the includes on your functions. I'm starting to experiment on this one in the pet project, and so far I'm happy with my code. As I mentioned, this library only is about 20 lines of code and like 120 lines of documentation. So this person is mostly very interested to give this idea out. So I hope that you give it a try and see how does it work. So I guess people don't have question about the lightning type, hopefully. So uh, so just want to thank you one more time for joining the Elixir Berlin Remote Edition, and I hope that you stay safe out there. We can hang out in the Discord channel if you like, and see you next month. Ciao.